Okay, here we go. So yesterday, the last we talked, we were talking about implicit differentiation. See that? This time, come over, just kind of a picture.
Of course you did.
Plus his
Your hands.
You know? Who wins in a fight, me or Mr. Viscount?
You don't even need to use like just break his brain with that.
Yeah, I don't know. I think he'd just like headbutt me. Right, exactly. That's all recorded. Fantastic. Right. I'll just run. Yeah. So yesterday we talked about implicit differentiation. Remember, implicit functions are all about, if we have our function defined with y in it, right? So, and we I kind of went off script a little bit and talked a lot about these. I didn't talk a lot about. We graphed these ones. These are just types of implicit functions. This is the kind of weird stuff that you can get with implicit functions. And remember, all of chapter 3 is about how we differentiate anything that we could possibly have. So we're talking about differentiating these as well. So we know how to do it, right? We talked yesterday about if we're trying to differentiate and we come across a y value and there's something acting on that y value, you have to treat it like a chain rule. You have to differentiate what's ever happening on the y and then tack on a y prime to it. If there's nothing happening to the y, well, then it just turns into y prime, right? Like for in this case, we had to differentiate the y squared, and it turned into, okay, differentiate those squared to knock down the power, 2y to the first, and then multiply it by the y prime, okay? So that was the rule that we came up with yesterday for implicit differentiation. If there's something acting on the y, you evaluate, you do the differentiation on whatever you're acting on, then tack on a y prime. If there's nothing acting on the y, just turn it into y prime. So if we can differentiate it once, we can differentiate it twice, right? So let's find y double prime of x to the fourth plus y to the fourth equals 16. Just so you guys know what this looks like, because again, I'm a nerd and I think this stuff is cool. This is what x to the fourth equals 16 actually looks like. It's kind of like a rounded out rectangle. Rounded out square. If we had x squared plus y squared is equal to 16, that would have been a circle with centered at 0, 0. This is kind of more of like a rounded out square centered at 0, 0. Okay. All right. So if I want to find y double prime of x to the fourth plus y to the fourth equals 16. Remember, y single prime will get me whatever the slope is around this curve. Okay, that's what y prime will equal to. So let's find it. So we're going to find d over dx of x to the fourth plus y to the fourth and d over dx of 16. Okay, distributing the d over dx, distributing the differentiation. Okay, well that's just 4x to the third. That's easy because it's an x value. I'm differentiating it with respect to x. And now, look, I've got y to the fourth. So I'm going to differentiate the to the fourth power, which means I get 4y to the third. Remember, leave the inside function alone. Y stays in the first part of the chain rule. And then multiply it by the derivative of y. Okay, y prime is equal to what? What's d over dx of 16? 0. Just like we had with our circle equation yesterday, I end up getting an equal to 0. Okay, sweet. I've got one y prime, so let's solve for that y prime. Subtract the 4x to the third over to the other side. I divide by 4y to the third. So that means we get y prime is equal to, the 4's will cancel, negative x to the third over y to the third. Okay, that's y single prime, right? Now let's find y double prime. Let's differentiate that. Now watch what's going to happen here. If I want to find, if I know that is y single prime, right? That is still in terms of y, right? I still have a function, I still have an implicit function as my first derivative. So it's going to be kind of trickier. When I go to find the derivative of y prime, well, that's what gets me y. That's what gets me y double prime. Okay? Now I've got to find d over dx of x to the third, negative x to the third over y to the third. Well, what's that telling me to do? Quotient rule. Okay, quotient rule is f prime g minus g prime f all over g squared. So that's going to be, y double prime is going to be equivalent to f prime g. F prime g. Now what I'm going to do is I'm going to take the negative all the way out. F prime g. What's f prime? 3x squared, and then times g, y to the third, minus g prime f. Okay, g is y to the third, right? You need me, Mrs. Apples? She looked like she had a question and she turned back.
Did you send a quiz you took yesterday and Sprout's one his?
That was a test and no. No. So I differentiate y to the third. So this becomes 3y squared times y prime. You follow me there? I'm differentiating the denominator. So it becomes 3y squared y prime. It's got a chain rule in it. 3y squared y prime times the original f. Divided by g squared. Okay. Y to the third squared is y to the sixth, right? Not y to the ninth. Y to the sixth. Power 2, power 2 multiply. Now, be careful here. I was just thinking, oh, I'm done. But I'm not really done. Because I misread this. I had to look at my paper because I misread this. Is that a y to the first? No, that's y prime, right? That's y prime. And you cannot leave a y prime within y double prime. It has to just be implicitly defined. But what is y prime? Negative x cubed over y cubed, right? So now let's say this. So this is negative 3x squared y to the third minus 3y squared. I'm going to pull the x cubed right in front of it. And now in place of y prime, I'm going to write negative x to the third over y to the third. All divided by y to the sixth. Yeah, I just rearranged it. I just pulled the x right in front of the. Okay, let's simplify that a little bit. So y double prime is equivalent to, we got negative, then we got a 3x squared y to the third. I'm going to take this negative and turn it into a positive, plus up top. And then we've got a 3, okay, y squared, and then I've got a times 1 over y to the third. So that's like y to the negative first, x to the sixth, over y to the sixth. Okay, now, I got to be honest. I would probably not give you anything past here. I would be very good if we got to here. But I want to show you that this one simplifies down even more, and there's something cool that happens when I simplify down a little bit more. Okay, I don't like so I am okay if we get to here. I'm going to box this answer because that's where I'm okay if we stop. But I want to show you what happens if we do a little fancy manipulation here. I don't like the y to the negative first. Okay, I don't like that y to the negative first. So what I'm going to do is I'm going to multiply by y over y. Y. Okay, now when I distribute that in, that's going to be a negative 3x squared y to the fourth. And then what's going to happen in my second term here? What's y to the negative first times y to the first? Cancels, right? Because if it's a positive exponent, if it's a negative 1 and a positive 1, and I multiply with my bases, I add exponents. This would have been like y to the 0, or just cancels out. So this ends up being plus 3x to the 6th all over y to the 7th now. What's my common term? If I were to remove a GCF in the numerator, what's my common term? 3x squared. And look what it leaves me with. Y to the fourth plus x to the fourth. What is y to the fourth plus x to the fourth equal to in this problem? Look at the very beginning. 16. So this actually ends up being negative, and then 3x squared times 16 over y to the 7th. So in other words, negative 16 times 3 is 48, I think. 48x squared over y to the 7th. That's cool. I don't know. I thought that was really cool, so I wanted to show you guys what happened there. My version is cool. But again, I'm totally fine if we had gotten to that point. That's really all I would ask you. This whole weird multiplying down thing, it just ends up being cool. All right. Now, if you remember on your formula sheets, okay, for derivatives, this thing, okay, on your derivative rules sheet, which I do have extra copies up there. If you need one, you can grab one. We learned all of the table. We learned all the top derivatives. We've got constant, the quotient rule, the product rule, and all that fun stuff. And then we've just recently learned the chain rule, which is also on there. But then we talked about derivatives of trigonometric functions, which is all on there too. And then on this whole box of derivatives of inverse trigonometric functions. Now, the reason we did not learn that when we were learning trig derivatives was because we actually have to use implicit differentiation when we invert the sine, cosine, and tangent. Now, I would show you the actual proof to all of these things, but I got to be honest, it would be easiest if we just learned them. Trust me, the proofs are all in the book. If you'd like to research those, if you'd like to look through them, I could explain it to you, but I fear that it would just go right over here, okay, right over the top of your head. So here's what I'm going to say. These are the derivative rules for inverse trigonometric functions. They are all right here on your sheet, okay? The derivative of inverse sine is, and now I'm going to kind of go over how I would memorize these, how I would think about these, okay? They all are in the form 1 over something, right? They are all in the form 1 over something. Sine and cosine are 1 over the square root of 1 minus x squared, except cosine is negative. Which, when we found the derivative of cosine, what was it? Negative sine. When we find the derivative of inverse cosine, it's negative sine. It's the negative derivative of whatever sine was. So that's one of the things that goes on in my brain. So if you know sine, negative of that thing is the derivative of inverse cosine. Now, tangent is when I take 1 over 1 plus x squared. Okay? So the minus sign that's inside the radical turns into plus, and the radical goes away. Notice that tangent and cotangent, if I take the derivative of cotangent, it's just a negative of tangent. Okay? Negative sitting out in front of cotangent that's not there when you have tangent. Now, we had the negative when it was cosine, and now the negative goes with cosecant. And I believe, and I'm actually just seeing this pattern as well. Yeah, this is cool. Think about back in our derivatives of trig, the cosecant, the cosine, and the cotangent all had the negatives, right? Same thing is true here. The cosecant, the cosine, and the cotangent all have the negatives in front. The sine, the secant, and the tangent do not have those negatives in front. Okay, now, cosecant and secant look very similar to one another, just like sine and cosine look very similar to one another. This is 1 over x quantity, square root of x squared minus 1. And notice that these flip when you go to cosecant and secant. This is x squared minus 1 inside there now. And then this is just a 1 plus x squared. Okay. So again, do your best to memorize these. And let's apply it now. I would have this out when you're doing your homework. Differentiate y is equal to 1 over inverse sine of x. Okay. When I go to differentiate this, I want to treat this, because this is 1 over sine x, 1 over inverse sine x, I'm going to treat this as y is equal to, why did I write y is equal to twice? Y is equal to inverse sine of x raised to the negative 1 power. Whenever you have something in a denominator of a fraction, treat it like it's a negative 1 power. Now, when I go to differentiate this, this is a chain rule. This is a chain rule. I have to differentiate the negative 1 power. Let's do that. Negative 1 times inverse sine of x raised to the what power? Negative 2. Multiplied by the derivative of inverse sine. Okay, we go back to our formula sheet. The derivative of inverse sine is 1 over the square root of 1 minus x squared. 1 over the square root of 1 minus x squared. Okay, so y prime is equal to, I'm just going to kind of condense everything. We got a negative, and look, this goes down into the denominator, right? The negative 2 exponent will push it down into the denominator. So this is 1 over inverse sine of x times the square root of 1 minus x squared. And I believe that's how we have to leave it. Oh, I'm sorry. To the second power. I brought it down to the denominator, and I just took out the power. We bring it down to the denominator, and that negative 2 exponent becomes positive. And that's where we're going to leave that. And now let's do part B. That was part A. Let's do part B. F of x is equal to x arctan square root of x. Now, what is arctangent? It's just inverse tangent. Right? Don't overthink that. Arctangent is just inverse tangent. It's just another way to write inverse tangent. So f of x is really like saying x times inverse tangent of the square root of x. Okay, now, what do I have to do with this? I actually have to use 2 rules. The first rule that I have to use, the product rule. f prime g plus g prime f. Okay, f prime. What's the derivative of x? 1. Okay, that's easy. Times the original g. Tangent inverse square root of x. Plus, okay, g prime. G prime. It is the derivative of inverse tangent of the square root of x. Now, when I go to do the derivative of inverse tangent, it's 1 over 1 plus x squared, right? 1 over 1 plus x squared. But that was if it's tangent of x. What do I have? Inverse tangent of the square root of x. Okay, so that's going to look like this. Well, what's going to happen with the square root of the x squared? It's going to cancel. It's going to have x. So I'm just going to reduce that right now to say just x. Now, that was the derivative of inverse tangent of square root of x. Now, because this is a chain rule, because I have a function within another function, I've got a square root inside tangent, I now have to find the derivative of the square root of x. Well, what's the derivative of the square root of x? Well, remember, this is like x to the 1/2 power, right? So it's 1/2 x to the negative 1/2. Okay, that was all just g prime. And now times f. Okay, so we've got, I don't know if I can do too much with this thing. So this is inverse tangent of the square root of x plus, now I'm going to write this here, 1 plus x, and this is going to be x over 2 radical x. This whole thing is simplified down there. Okay, I put the x in the numerator. You know, that's what I have written down. I think I can make this cleaner. Hold on a second. Hold up. Because, what can I make that? Aren't I multiplying with bases? Can't I just add exponents? So what is x to the negative 1/2 times x to the first? It's the square root of x. X to the positive 1/2. Now don't forget the 1/2 sitting out front. So it's the square root of x over 2. Okay, now I'm just going to multiply. So we got inverse tangent of the square root of x plus the square root of x over 2, 1 plus x. And you know what? That's where I'll leave it. We'll leave it there. Questions about that? Okay. Well, I am going to stop the video, and I'm going to let you work on the rest of we'll let you work on the homework the rest of the period.